last speaker in the session. We have Hyungrok Kim, who will be telling us about L-infinity algebras, hopefully in English. So go ahead.
Thank you. Hi. Yeah, don't panic. The rest of the slides will be in English. So the famous French philosopher Stephen Colbert once described the Eurovision Song Contest as Euro, like Australia, and vision, like sound. And Voltaire said something similar about the Holy Roman Empire, remember? So here I am at Eurostrings, and I'm from South Korea, which is European, and I will be talking about homotopy algebras, which are stringing. That wasn't quite fair because these homotopy algebras actually did originate from string field theory. But it turns out lately that these gadgets turn out to be more broadly useful, or they describe high symmetries generally. In particular, I will talk about how Yang-Mills theory, our favorite theory, can be inoculated with these funny homotopy algebras in two different ways. Good. So English is promised. So let's start with super Yang-Mills, Maxwell super Yang-Mills, which is lovely, nice, pretty. Let's make it up to 10 dimensions, which is the largest dimension it exists in. Now, there's a nice procedure to make something that's lovely, even lovelier, which is just twist it. So you pick this particular nice symmetry, that squares to 0, and then you look at the subsector of Q-closed things. And then what often happens is that these Q-closed things are then the correlators of such operators and obey more symmetry. They can be topological or just holomorphic. And Q-exact things end up vanishing, so you get a Q-cohomology. Now, there's a fancy way to do this, due to Kosow-Emley, So you start with your favorite symmetry, which in our case will be super Poincare. Now, this is a super Lie algebra, so it's originally graded just even and odd. Now, for technical reasons, it's convenient to lift this even-odd grading to an integer grading. And then also for technical reasons, it's convenient to complexify, essentially because you want to get holomorphic kind of stuff. And then what you want to do is pick an element of degree 1 that squares to 0, and then add a differential on it. Now, after doing this, then now you have a not just Lie algebra, but a differential graded Lie algebra that I'm going to call PQ. This is the twisted symmetry algebra. And then you take the cohomology. And the cohomology is supposed to tell you the symmetries, the non-trivial symmetries of the remaining of the twisted theory. So for example, if you do a topological thing, then if you do a topological twist, then this is not going to contain any translations anymore because translations are just, everything's just invariant. And if you do the holomorphic case, then this will only contain holomorphic translations, DDZ, but not DDZ bar, the anthomorphic translations. And for example, the twists of n equals 2 SCFT, for example, that Chris talked about earlier, can all be formulated in this kind of language neatly. So let's continue. So for 10D, we start with super Poincare, and then complexify. So in this case, the Q squared to 0 condition just amounts to this funny equation, which if you're familiar, or you might recognize as a pure spinor condition. So you pick up your spinor Q, and then follow through the steps, and then you get this. So originally we had super Poincare. These were translations, these were Lorentz transformations, and these were the super translations. Now, having chosen such a Q, it turns out that this defines a complex structure on your 10-dimensional spacetime. So in particular, you can pick out an SL5 subgroup of O10. And so now we can decompose everything into SO5 ERAPs rather than O10 ERAPs. And then it turns out the things decompose like this. And then, when you turn on this differential, then it turns out that the differential maps this to this, this to this, and this to this. So these become Q-exact, and so go away in the cohomology. These become non-Q close, and so go on the cohomology. And what survives is this bit. Right. So, and most of this actually makes a lot of sense. So let's pick holomorphic coordinates on my 10-dimensional, so 5 complex dimensional spacetime. Then you have the holomorphic translations, and then you have the holomorphic SL5 rotations. But then, what is this? Where did this come from? All of that. So to do this, I have to use a dirty word, unfortunately. The dirty word will be an L-infinity algebra. What it is, but don't be scared. So what it is just a differential graded Lie algebra. So it's a Lie algebra that has integer grading, that's differential, and such that the Jacobi identity that we all know fails. That's bad, but in a controlled way, which is good again. So what you do is it's a fancy way to say that it holds up to homotopy. So in particular, and once you have this, then you can actually organize all this data in a kind of nice fashion. So differential we call mu1, and in the Lie bracket we call mu2. And the thing that controls the failure of the Jacobi identity we call mu3. Also it's a ternary thing. And then that thing in turn has a higher order kind of coherence relation, which once again fails in general, but only up to some controlled thing, which is mu4, which is some quaternary thing, and so on and so forth. Now, what makes this thing nice is that if you start from a DG Lie algebra and take the cohomology, now the cohomology is going to carry the structure of a graded Lie algebra, that's fine, but in fact it carries more information. It carries canonically the structure of this nifty gadget called an ln algebra. So back to our story. So we started out with 10 Yang-mills, twisted it, and then got this funny symmetry thing. Now the theorem tells you that this funny thing is supposed to carry an ln algebra structure, and indeed it does. So this thing then has this higher bracket mu4. And right now, 10-dimensional. If you twist 10-dimensional super Yang-mills, this is supposed to give you a 5-dimensional Homotopy-Chern-Simons theory. Now, if you saw this, if someone gave this action to you, you see, oh, well, this looks holomorphic. There's a Calabi-Yau form, so it has to be invariant under whatever homomorphic transformations that respect this Calabi-Yau form. And, well, you'd be right. But what you wouldn't know, unless you came from this twisting perspective, is that this thing actually comes with an extra higher structure. This thing comes with this bit of extra structure. And you can't really see this just from the steering of the action because this only is visible in the higher components of the section. So there's a sense in which this thing carries its higher symmetry. There's a notion of LMT algebras acting on fields. And this extra bit does act non-trivially, but only in a higher sense. Right. Now for the second thing, I'm going to tell you something slightly crazy. Okay, you've heard that on the one hand, there's holography. That AD is 5, gravity is AD is 4 Yang-mills, yada, yada. And then there's double copy. Yeah? Now, what you haven't heard is that, say, gravity, say with a background stress tensor, is literally Yang-mills. That's kind of insane, right? Yeah, don't worry, don't call security just yet. Yeah, so this sounds kind of crazy. But let me tell you what I mean. So it's been known for some time, since like ages ago, that 3D pure gravity is topological and is equivalent to a Chern-Simons theory due to Ashokar and Townsend and Witten and so on. Where what you do is you start from a particular Chern-Simons theory. If you want zero cosmological constant, that happens to be this. Where this double struct A decomposes into these two components, and then in terms of this, then you just get a nice BF theory, right? And then, now these two components, if you compare it to the usual 3D gravity action in a first order formulation, then E is the dry bind, and omega is a spin connection. And then you see that if you match this and this, then you see that E goes to A tilde, and omega goes to A. Right? Nothing surprising happening so far. Both sides are topological, no degrees of freedom. Right? Now, let's add this funny term. So which is a double struct A, which star A. So it's like this squared. Notice that this requires using a background metric. So to do a Hochstar using the background metric, which I'm going to call G hat. So it's no longer topological theory. In fact, it's easy to see that this is actually the usual first order formulation of Yang-Mills theory. If you integrate out this A tilde, then you get the standard Yang-Mills action in 3D, which definitely has degrees of freedom. On the other hand, let's take this action and translate it according to the previous dictionary. So A tilde goes to E. And this should have been, A. There goes spin connection. And then there's this thing where supposedly I write the inverse of background metric as T mu nu, because maybe I like lots of T. Then you see that this thing then looks like a background stress energy tensor. It's T mu nu, G mu nu. So, yeah, right. So this is a sense in which 3D gravity with a background stress energy tensor, which is non-dynamical, is precisely equivalent to Yang-Mills theory in 3D, where the background metric then goes to a background stress energy tensor. So this is all very nice, but no sign of LNPT algebras yet. How much time do I have? 5 minutes, great. I'm going slightly faster than expected, so maybe I can talk more. So what you can then do is, let's complicate things. So there's a generalization of Chern-Simons theories called AKSZ theories. These are funny gadgets associated to what I call symplectic L-infinity algebroids, which sound very, very scary. But yeah, they're just a pseudo generalization of Lie algebras within diametric. The symplectic structure is a generalization of a metric. And in particular, empty algebras are a special case of these things. And so what you can now do is take this pseudo generalization of AKSZ theories, which are topological, and then add mass-like terms, like we did before. And then the game is to then see which of these cases give you gravitational things. Right. And it turns out that in a surprising number of cases, you can actually get this to work. So in 3D, apart from, so we started out with Yang-Mills theory, and then we got ordinary GR plus a background, right? Now, it turns out that we can use a slightly different structure, this Lie group with whatever. And in that case, you get, if you interpret it as just ordinary gauge theory, well, ordinary theory, then it turns out that this gives you well, actually, this isn't quite right. This should be ADS2 nonlinear signal model. I think this is a typo. Right. Whereas if you think for the gravitational theory, then you see that this is Einstein-Cartan plus this funny thing, which this direct coupling, nominal direct coupling to the spin connection. So what that does is it relaxes the torsion free constraint of your theory so that you get some funny Einstein-Cartan thing. Right? And similarly, now if you do this in this slightly different way, then what you get is the so-called third-way gauge theory, described by Abratakis 7,000 some time ago. And this funny thing arises as a particular subsector of ABJM model of M2 brains in some kind of Romance background. Right? So it's like some legit stringy thing. But then this thing now corresponds to general relativity with a positive cosmological constant and coupled to a background metric. And similarly, if you want a negative cosmological constant, so you can do that too. Then you get what's known as an imaginary third-way theory that was recently described in Abratakis Kanakaris recently. Now you can do this in 2D as well. AKSZ theory exists in all dimensions. And if you do this in 2D, then it's on the one hand, in 2D it's well known that JT gravity is the equivalent to some kind of BF model, which is a special case of AKSZ. And then if you, depending on how you play the game, on the other hand, you can either get a nonlinear signal model or Yang-Mills theory. And then these, in turn, correspond to JT gravity with either a background stress energy coupling to the string frame metric or to some kind of funny dilatonic quadratic dilaton potential plus some relaxation of the torsion precondition. You can also even play this game in 4 dimensions. The other story is a little bit more complicated. There you get some slight generalization of the Blavatsky formulation of 4D gravity. And then, if you interpret this as a gauge theory, then you get 4-dimensional Yang-Mills coupled to a bunch of scalars. And if you take the mass of those scalars to be very large, then those scalars become approximate Lagrange multipliers, such that you get 4D gravity coupled to a background rank 4 tensor, coupled to a metric in a funny fashion. Right, how much time do I have? 2 minutes. Okay, great. Well, since I have this extra time, let me show you some slides. Yeah, so in the 3D case, generally, you get things look like this. You get Chern-Simons, you get Yang-Mills-like things, plus some funny-looking extra terms. And these things give you nonlinear signal models. You can realize general non-homogeneous, homogeneous space nonlinear signal models. And these third-way theories, imaginary third-way theories. And these give you gravitational things. In the 2D case, similarly, you have a BF formulation of your of JT theory, and then similarly, you write a mass term, and then these mass terms then under the usual dictionary then goes to a background stress energy tensor. And if you do a 4D thing, then with this funny particular gauge algebra, then you get something that's nearly the Blavatsky model. So if you add some appropriate mass-like terms, and then integrate some fields, then phi becomes very heavy, so that, and then when phi becomes a Lagrange multiplier, then this is the Blavatsky formulation gravity, such that you get gravity. Whereas if you regard as gauge theory and figure things out, then you get Yang-Mills plus 20 scalars coupled in a funny way. Yeah. Yeah, and I guess you get to go to snacks earlier.
Questions?
Yes.
I have a perhaps the plebe question. In this final collection of statements you were making, you were saying the word corresponds. There was a correspondence between these gauge theories and gravity theories.
Yeah. So yeah.
Can you elaborate on?
Yeah.
Is this an isomorphism of classical field theories, or
it's
quasi-isomorphism of some DG field theories, or like what is the really going on here?
In the plainest possible sense that they have the same action. So in particular, they have the same solutions to the classical equation of motion. I mean, the kind of quibbles you can put in this are for gravity, then you should really sum over topologies and have whatever gauge transformation, yada, yada, yada. So this should, and then for gravity, you should ensure that the metric is non-invertible, whereas in this Chern-Simons formulation, you have degenerate metrics. And so you can show that, so apart from such things, so at least they start to hold classically, at the classical level, this is just a complete equivalence of classical perturbative theories. So in particular, you have Yang-Mills solutions, and then you can then view these as gravitational things and vice versa. So if you have, so you can find like black hole-like solutions on the gravitational side, and then then this corresponds to a funny solution of 3D Yang-Mills.
And is this related to or completely distinct from some like double copy types of statements?
As far as I can tell, yes. So double copy, so holography has, the bulk and boundary things in different dimensions. These are just the same dimension. And double copy, well, it's not that Yang-Mills solutions are literally gravitational solutions. You have to take Yang-Mills solutions, and then, if you don't want to do classical double copy, then you take Yang-Mills solutions or particular ansatz, and then double copy to get gravity in the Kerr-Newman or whatever ansatz. But this is not that. It's just that you take Yang-Mills solution, you just translate the variables, A goes to like field dry-bind or whatever, and you just get a solution to Yang-Mills. No like double copy or anything needed. Yes, please.
I know that you were talking about classical equivalences.
Yeah.
Yang-Mills in 4 dimensions, I think. Well, gravity in 4 dimensions is not renormalizable. I know that I'm going to go away from classical.
Yeah.
How does this make sense if gravity is not a renormalizable theory?
Right.
It's not good in the UV, but the Yang-Mills side is fine. I don't know.
Well, I mean, the Yang-Mills side, in terms of mass dimension counting, it doesn't, if you're in, if you're trying to quantize this, well, one thing I can tell you is that if you want to think of it gravitationally rather gauge theoretically, then the notion of what the vacuum is actually quite different. In the Yang-Mills case, you have the vacuum is just A equals 0. And if you translate under the dictionary, then this corresponds to G mu just equals 0. So there you're perturbing about some very degenerate thing. Whereas, so you were talking about how perturbation theory, etc., makes sense, if you want to do quantum things. Yeah, the short answer is I don't really know, but the longer answer is that these might correspond to perturbation theories in 2 very different regimes.
maybe this is related to the question that was just asked before. There are also some results about double copy saying that Yang-Mills squares to double field theory using these homotopy algebras and the infinity. I'm not sure.
Yes. Yes, I'm aware
Are
of
you
them.
making similar statements, or they are completely unrelated?
Yes, so yeah, the homotopy double copy story, yeah. I'm aware of that. I wrote some of those papers. As far as I can tell, I don't think they're related. I mean, it might have, I mean, one thing that could, yes, so the short answer is I don't see any obvious connections. I mean, one thing that you could try to do, if you want to relate it to usual kinds of graphic correspondences, I mean, so you get solutions to these things, Yang-Mills and whatever these other things, living on ADS. And then you can then see these as gravity with some funny stress energy background. So then you have the kind of crazy idea that, can you like have like some boundary dual to just Yang-Mills, which on the one hand sounds kind of crazy. On the other hand, there's almost apparently some recent work by like Bertolini and Maggiore and whatever about boundary, whatever theories correspond to Maxwell-like things. So. But yeah, double copy, I don't know if there's any relation.
Thank you.
Okay, let's thank the speaker again.